these before. So a power function is an equation that contains a power, meaning we have an exponent, but the variable is going to be the base of this exponent. Like my example, I have y equals x to the fifth, or the most common y equals x squared, which would give us a parabola. Okay, so we're pretty used to working with something like that. Today we're talking about exponential functions where we're still working with powers, but the variable is now going to be the exponent. For example, y is equal to 5 to the x power. So the variable is going to be our exponent. Okay, so we've got the parent function of exponential growth, and we've got exponential decay. Notice that exponential growth goes up and up and up and up and up forever and ever and ever and ever and ever and ever. We have an asymptote. In this case, in the parent graph, the asymptote is the x-axis, where it's going to get closer and closer and closer and closer and closer to the x-axis, but it's never ever ever going to reach it or cross it. Okay? Exponential decay starts from a really, 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 really big number and goes down and down and down and down and down and down and down, and gets closer and closer to, in this case, our x-axis again, but won't ever quite get there.
So you might try to find out when x is 0, when y is 0, what would x be?
When y is 0.
Decay.
Oh.
You just try to find what the y and x intercept is.
It will never be there. There is no x. Okay? Notice that for exponential growth, our base number b, whatever that constant is going to have to be greater than 1. But if it's decay, then it's between 0 and 1. So in other words, if I had something like y equals x, okay, I know it's going to be a growth function. But if I had y equals like a fifth to the x, then I know it's going to be decay, because if it's between 0 and 1. Does this make sense so far? Okay. So example 1 asks us to graph these three functions on the same set of axes, meaning on the same graph, and then compare and contrast them. The easiest way to do these, I think, is to make a table of values. So let's click the table of values for this one. I would usually probably start with -3, -2, -1, 0, 1, 2, 3. Okay, so you're going to take a calculator. We're just plugging in. Remember, we're going to plug in for the exponent. So
-3 is the x or the y?
We're putting in some of the x to find the x.
So it would be 4
Well, not 4 times -3. 4 to the power of -3. So it's going to be a big, long, yucky thing.
What?
It's going to be a big, long, yucky decimal, right?
Is that 0.015625?
You're right. So I'm just going to round it up to that. Okay, now let's go forward to the -2.
I didn't get that.
You didn't get.
Oh, wait, no.
I rounded it. It's a.
I got the.
That is a 0. I thought it was a 0.
Oh.
Oh, it's a 0.
0, what?
0, 1, 5, 6. So really, really close to 0, right? Yep, sorry, that was 0.
0.0625.
Put 1 in there, -1, yes.
0.25.
How about 0? We can do that without doing our calculation. We can do 0 power is
0, 1.
And we can do 1 there. That's 2. 4 to the 1 power is
4.
and 4 squared is, and 4 to the 3rd. Okay, just by looking at our table of values, I know this is a exponential growth, and just by looking at the equation, we know it's a growth because our base 4 is greater than 1. So if we were going to graph it, -3 is almost 0, so it's practically there. And it's practically on 0, -2, and almost, but not quite 0, at -1. So then we've got 0, 1. We've got 1, 1, 2, 3, 4. and 216 something way over here.
All we do is kind of move it up and down on the relative to the x there.
Well, I don't know. Is that what's going to happen? Because if we're going to do table of eggs for this next one, yeah, we've already plugged in the first part. We've already got the exponent done. All we need to do is add 2 to everything.
Give me that.
Because our regulation tells us to do that. Yep. So we have 2 by O.
Could you just do it on the graph now?
Yeah, I'm just showing that this, if you didn't realize that all you had to do was move it up by 2, but yeah. Yeah. So in our first one, our asymptote was at the x-axis at 0. What's our asymptote in this case? 2. Yep, 2.
So whatever number.
2. How did you know that?
Because it's, if I kept going with the negatives, if I go -4, -5, -6, and then get closer and closer and closer and closer to 2. Because my graph is just going to keep going closer and closer and closer to 2, but not actually going to get there.
Okay.
Is this, do this totally calculate because it's too big of a number to handle? So I did 4 to the negative, really big number.
Yeah, it's such a tiny decimal that it's not going to handle it. Or, wait, you did what?
4 to the negative, that really big number.
Yeah, it's such a tiny little thing that your calculator can't handle it. Because remember, negative exponent is a the fraction, so you're saying really 1 over 4 to the thousandth power. Which would be really tiny. All right, what happens with this last one? How would we graph this one? And we could make it to brackets, but we won't have to because what is it going to look like? Well, let's think. With this one, we just had 4 to the x. We found all those places to figure out what is down value. Right, because we added 2 to go up 2, so we're going to minus 3 to go down 3. So where's our asymptote in this case?
3.
-3. Yep, you got it. So compare, contrast, compare, there is that the same shape, right? Contrast would be they have different asymptotes depending on where you're going to move it up. Questions, comments? All right. On the next one, same idea. We won't have to graph all these, so I think you guys understand. But what is going to happen, because we have graph, but then we have 6 and -2. Is that going to move it up 6, left 6, stretch by 6, compress by 6? What's going to happen?
It's going to be over.
Yeah, it's going to stretch it. It's going to stretch it. It's going to pull it, so it's going to look really big going up and down. If we were going to graph it, is it going to be exponential growth or decay? Decay. How do you know? Because it's a fraction. Our base is
What was the negative 2 do to make like this?
The -2 is gonna, well, the negative is gonna flip it upside down because decay goes this way. Negative is gonna flip it, so it's gonna go reverse that way. So, and the 2 is gonna stretch it vertically.
The first 2 are going to go like that.
Yes.
So fractions.
Fractions decay. Do you guys want to graph these? you guys understand what we're doing?
Yeah.
Yeah, what?
That's good.
Let's graph it. Let's do which table values. And I will just start with our -3 to 3.
So you just take. Oh. How do you?
You're gonna have to put them in parentheses or go 1 divided by 5 equals and then take that to the power.
What are you going by?
I just went by ones. So all I really do graph is the -1, 5, 0, 1, and try to get 1.
How do you get that? Because if you go over -3 up, it's bad.
Right. It's way off the graph, so I didn't even pay attention to it. I just know it's going to start way up here and come down. And then make this. Okay, so Caleb, all I did was this one's way off our graph,
Yeah.
this one's way off our graph. So I started with this one. So
Um,
-1, 1, 2, 3, 4, 5, and I know it's coming from way up there. So what's our asymptote in this case?
0.
0. Okay, so then let's see if we can graph this guy. So since we've already found the exponent part, all we have to do is take all of our numbers from our first table and multiply them by 6. So this one's going to stretch it really far going vertically, because if I multiply by 6, I get even a bigger
So
line.
we're multiplying, say y equals 1/2, 1/5 to the x. Would that squish it?
1/2 would squish it, yeah, it's squishing this way. Okay? Good question. Okay, then again with our other last one, all you have to do is take our numbers from the first table and take them times the -2. In this case, since it's a negative, like I said, it's going to flip it, so it's upside down. So So -3, -250, somewhere way, way, way down here. I'm going to start with -1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, somewhere there. Almost. Oops, let's go -2. All right, questions, comments? All right. So exponential growth and exponential decay, usually they're used to model population growth. Usually populations grow exponentially because if you, like, anybody have pet rabbits or anything? No? Okay, well, we know that rabbits like to have lots of babies, and their babies have more babies, and their babies have more babies, so they grow exponentially because for every one rabbit, they may have 3 or 5 or whatever in the litter, and then those 5 or 10 or whatever in that litter are going to have more babies of their own, like 5 or 10 each for them, so it's going to grow exponentially. Does that make sense? Rather than just doubling, it's exponential growth. So usually we set it up so it looks like this or like this. Notice they're exactly the same, except growth is your adding, decay is your subtracting. So A is the initial amount. So in other words, if we were only going to start with 2 rabbits, that would be our initial. A would be 2, whatever you're starting with. Your R is the percent of increase, how much is increasing each time, and then T is going to be your time in years or months or weeks or whatever your time period is. So the base of the exponential function, whatever's in this parentheses, is the growth rate. And the decay is the decay rate. Okay, so let's look at example 3. It says there are some years beekeepers have experienced a serious decline in the honeybee population in the U.S. One of the causes for the decline is the arrival of the varroa mites. Actually, that's how you say that. I'm not sure. The experts estimate that as much as 90% of the wild bee colonies have been wiped out. Supposedly, researcher estimates that the initial population of these kind of mites in the colony is 500. They're increasing at a rate of 14% per week. What is the expected population in 22 weeks? All right, so this exponential growth or decay? Talking about these mites. Growth. Okay. Then we just need to plug in what we know. So
Do you, which one, what do you use a T on? Do you use a T on everything or just the one minus?
oh, it's only what is in the parentheses goes to that pattern. Okay, so A is our initial. What's our initial?
500.
That's what we're starting with. What is the rate of increase?
1.4.
And we want to put that, the percent, put it as a decimal. So if we want to, we could already just put these together and say it's 1.14. To the, what is the time that happens?
How'd you get 1 point?
Because the rate is 1.14.
Yeah.
But I'm adding 1, so it's
Why do you add 1?
because that's what it says to do right here. Add 1. All right, how many weeks do they want us to do this by? 22, so that will be our power. You have to be careful on how they word things because sometimes they'll say they're increasing at a rate of 14% per week and they want to know what's the expected population in like months or something. So make sure you put them in the same, whatever the rate is, whatever the percent per whatever, make sure that your T is in the same.
So if it says they're raising the rate of 14% per week, but any expected population in 4 months, then you look at 16 power.
Right, because, well, not 16 power, we would want to go 4, and then how many weeks in a, so, oh, it was 16. You're right, yes. Does that make sense? Okay, and then what do we come up with?
3,930.
Okay, any questions on how we set that up? Yes, compounding interest, we got another formula. It looks really similar to our exponential growth. The only thing that is different is this, we have our rate divided by n, where n is the number of compounding periods each year, and then also that affects our t up here, we take n times p. Okay, so A is the amount that we're going to have every time after we figure out the interest. So P is still the principal amount, so we still have whatever we're starting with, whatever we put into the account at the beginning. R is still the interest rate, so it's still going to be a percent divided by however many times they compounded in a year. Does this make sense so far? All right, let's see what we can do here. Example 4 is determine the amount of money in a money market account providing an annual rate of 5% compounded daily if markets invest $2,000 and left it in the account for 7 years. So I would like to just write off to the side here what everything is. So what is our P? 2,000. So $2,000 in this account. What's the R? And I'll put that back as a decimal, so move it over twice, 0.45. All right, how about the N? Why is it 365? Right, it's compounded daily, and they want to know how many times in a year, so 300 a year, or 365 a year. Okay, how about T for time? 7 years. All right, then you should plug everything in. Okay, what I would do first is I would figure out the fraction and add 1. Make sure that you put these in parentheses. If you don't figure out that first, your calculator won't know what you're doing. This is what I'm coming up with. Check that.
Inequality.
We don't have that in house. Yep, graphing inequalities are exactly like what we did when we graphed at the beginning. The only thing that's different is you have to watch out and make sure that you make it either a solid line with or equals. If it's not an or equals, then we need a dotted line, and then you just have to shade one side of the other. Okay, so if this was an equals, we're going to treat it like it's an equals and make our table values. Again, I would go with our standard -3 to 3.
We're going to take 2 to the -3 plus 1.
Make sure you do exponents before you add. Order of operations. Okay, so let's do the table values and we can plug our points in. solid line or a dashed line? It's going to be dashed, right? Because it's not an or equals, it's just a less than. Okay, and then we need to figure out if we're going to shade below it or if we're going to shade above it inside line. Okay, come up with what I'm going to put in. So in order to figure out which,
How is 0 and 1? And
oh, it should, is it 2? What's it?
because if it's a
Yeah.
It should be 2. I'm sorry. Forgot to add the 1. That changes my graph.
Totally crazy.
well,
I'm sorry. I'm sorry. Graph.
why does that have to be done?
Because it's just a less than, if it was less than or equal, if it was or equal, then it would be a solid, but less than or greater than are just dotted, because they're not included in the solution set. Okay, now if we figure out which side to shade, I think it's the easiest is to plug in 0, 0. If it's true, then we shade this way. If it's not true, then we shade on the other side. So we plug in 0, 0 for x and y. So this is what we would have. So I would say, okay, 2 to the 0 is 1. 1 plus 1 gets us 2. Is this a true statement? Yes, 0 is less than 2. So yes, I want to shade where 0, 0 is. So we want to shade everything. If it did not make it true, then we would want to shade on the other side of the line. All right, I think that's the last one. Any question on things?